Today I will talk about a project in collaboration with Professor Caye Silva from Federal University of Goiás. I call project because there are some directions that you can follow after the result that you get. And this project started in 2019 when I was in Goiânia for a postdoc. And in that time, Professor Caye was studying a technique introduced by Professor Yavdat, who was there as a visitor professor. And our purpose in that time was study equations, indefinite equations. In this talk, I will discuss on this class of equations P here. The main feature of this class of equation is the presence of a function that changed the sign. So we are interested in the definite case. And we look for existence of solution for solutions in this class of equations. And firstly, naturally, the solution depends on the parameter lambda. And there is a vast literature on the existence and multiplicity results for solutions of related equations to P over the presence of Laplacian operator or other functions. And mainly when lambda is less than the first eigenvalue of the Laplacian. But when you consider the parameter lambda greater than the first, bigger than the first eigenvalue, the strategy to get solution is more delicate. Okay, so in that time, Professor Caye was studying the extreme value lambda star that I will introduce later, and our purpose was to analyze what happens when we introduce lambda star in that equation, and if we get solution when the parameter is equal to lambda star and bigger than lambda star. But before talking about our main result, I would like to introduce a brief survey on related result that motivated our work. Okay, because we have to be clear what is the contribution and what the presence of the lambda star in the equation do. Well, as far as we know, the first to work in this direction is this one from Young. And when the author studied problem P in the following case, the author considered a bounded domain, considered the Laplace operator, function h equal to 1 and g equal to a power. And the authors prove that there exists a parameter lambda 0 in such a way that if lambda is less than lambda 0, then you get a solution curve, okay, starting at the origin, and you get this pair lambda u lambda for any lambda less than lambda 0. The author also studied when P is between 1 and n plus 2 by n minus 2, and he got two distinct positive solutions for problem P. If lambda is equal to lambda 0, then he got a unique positive solution. He proved that there is a unique positive solution for problem P. And if lambda is bigger than lambda 0, there is not any positive solution for problem P. This was in 1991, but in 1993, we have this work from Alama Tarantello, very famous one, when the authors considered a bounded domain, once more the Laplace operator. And it's important to say that the negative part of f, remember f changed the sign. So The negative part affects the problem when lambda is greater or equal than lambda 1. And this work is very interesting. There are very interesting remarks there. And a very interesting fact pointed in this work is that this problem 1 here, in the presence of the first eigenvalue here, admits positive solution if and only if condition 2 is satisfied, where this function is the first positive eigenfunction of the Laplace. Okay, so if you are studying equation 1 in the presence of the first eigenvalue, naturally you have to require a condition 2, as we will see before. We will see later. Okay, so you have this equivalence here. In 1996, Singolan Gamez studied problem P in the following case. They consider the whole space Rn, the presence of the Laplace operator, G is a power, and they proved the following. If lambda is between the first eigenvalue, this is the first eigenvalue of the problem with weight H. Is the first eigenvalue, then P admits at least one positive solution. If that condition 2 is satisfied, then there exists a positive epsilon such that if lambda is between lambda 1 and lambda 1 plus epsilon, then P admits at least 2 positive solutions. And that solutions are obtained by mountain pass theorem and minimization method. 1996. 2001, Costa Terani considered the problem in the whole space Rn, Laplacian operator, and G behaving like a power at 0 and at infinity. They also required a condition at infinity of F. Remember, F changed sign. And they proved that if lambda is between the first eigenvalue, then P admits at least one positive solution. And if that condition 2 is satisfied, then P admits at least 2 positive solutions. Okay, so the authors obtain solution when lambda is a little bit bigger than lambda 1. But it's important to say that in all of these works, it was necessary to require a condition in this set omega 0, because remember, since F changed sign, you have to be careful when in the set when F is positive, negative, or equal to 0. In all of these works, it was required. It's called thickness type assumption. Okay, is this one here in this box. And in 2008, Chabrowski and Costa studied problem P without requiring thickness type assumption. Okay, this work was the work that motivated us to study this class of equations. Remember, Chabrowski and Costa are studying equation in the presence of P Laplace operator. This function here changed sign, okay, and they are not requiring thickness assumption. And they obtain the following. If lambda is between 0 and lambda 1, you have one solution via minimization. If lambda is equal to lambda 1, then you get a mountain pass solution. But there exists delta, a positive delta, such that if lambda is between lambda 1 and lambda 1 plus delta, then you are able to obtain 2 solutions via minimization method. And you are minimizing in the components of the Harmonic that I'm going to see to explain later. So, and Chabrowski and Costa also studied non-existent results if you don't have that assumption in the integral involving the eigenfunction, or if lambda is very large, then you have non-existence result. Okay, so our goal was to consider the same equation studied by Chabrowski and Costa, but as I said before, we want to analyze what happens when we are in the presence of the extreme value of Nehari manifold, lambda star. And our idea was to adapt a technique introduced by Professor Yavdat and studied jointly with Professor Caillé, involving fiber method of Porosaiv, as I will say later, and compare with the work that with Shabrowski-Costa's work. So we have to make very clear to show the difference between the parameters that we are considering with the parameters that Shabrowski-Costa considered. Okay, and this lambda star is the so-called extreme value of the Nehari manifold method. This infimum here, and the name extreme value of the Nehari manifold is because this lambda star defines a threshold for the applicability of the Nehari manifold method. In the following sense, if lambda is strictly less than lambda star, then you are able to apply minimization directly on the Nehari manifold. But when lambda reach lambda star, you have a problem, because maybe the Nehari manifold may not be a natural constraint to your problem. So if you minimize there, you have to be careful if the point that you get is in fact a solution to your problem. So in this parameter, we have the big difference in between these two works. And we consider the following assumptions on F. Assumptions F1, F infinity, and F1 are the same assumptions required by Shabrowski and Costa. F1, F infinity, and F1. The difference here is the presence of assumption F2. This assumption F2 is a thickness type assumption. And we need this assumption to deal with the problem when lambda reach lambda star. And this is the main result. Firstly, we prove that lambda star is bigger than lambda 1. To the problem makes sense. And there exists a positive epsilon such that we have two solutions for problem P when lambda is between lambda 1 and lambda star plus epsilon. But see, Shabrowski and Costa obtained two positive solutions when lambda is between lambda 1 and lambda 1 plus delta. So we have to make clear that lambda star plus epsilon go further than Shabrowski and Costa. So the idea makes sense. So we have to concern this. And some remarks are important before to start the method, is that we are assuming that H belongs to L and P, and by P, because in the presence of this assumption, we have that this functional is completely continuous. Okay, so this assumption is very important in our approach. We are dealing with the problem. We look for solutions via variational methods. So we are going to introduce an energy functional, and you have to understand the natural space to our problem. Since we are dealing with lambda greater than lambda 1, then we are going to D1P. But remember that D1P is embedded into LP star, but may not belong to LQ. When Q is between P and P star. So the natural space to work in our problem is D1P intersectional with L gamma, endowed with this norm here, okay, to get the well definition of the functional and to apply variational methods. Here we borrow the ideas from Shabrowski and Costa. Then we introduce the energy functional. The energy functional is well defined. We define H lambda and F, and following Shabrowski and Costa. Remember, we do not have compactness, so we have to recover some compactness. We are dealing with the problem the whole space, so we have a lot of problems. And following Shabrowski and Costa, we introduce these quantities, alpha infinity and beta infinity, 3 and 4. And in view of 3 and 4, we have 5, 6, and 7. And remember, we have an assumption in F infinity. In fact, we are requiring that F infinity is negative. So this is very important in the proof of our results. Okay. Well, our approach is based on a Hardy manifold. Okay, we introduced the Hardy manifold in a standard way, and lambda. We split the Hardy manifold into 3 components, n lambda plus, n lambda minus, and n lambda 0. And using the notation that we introduced in the previous slide, we may write n lambda plus in this way: h lambda negative and f negative, n lambda minus when h lambda is positive and f is positive, and n lambda 0 when h lambda is equal to 0 and f is equal to 0. And we need to understand what are the properties that this component bring to us. Because see, firstly, if the components n lambda plus and n lambda minus are non-empty, then these components are C1 manifolds of codimension 1. Moreover, the union is a natural constraint to our energy function. So we are able to minimize in there. But look, if lambda is between 0 and lambda 1, then you have only one component, n lambda minus. So in this case, if you look to the fiber map, if you have the fiber map aqui, phi lambda TU, then you can find the maximum point. This behave like this. You have a maximum point. But if you consider lambda between lambda 1 and lambda star, you have 2 components. So if you look to the fiber map, you may find a maximum point and a minimum point. Né? You can find a maximum and a minimum point. The problem is when you consider lambda greater or equal than lambda star, you have 3 components. So you have to be careful, because in the presence of the n lambda 0, you don't know if the point that you get, in fact, you don't have a natural constraint to your problem. So you have to be careful in this case. So what we do? We introduce the minimization problem into each component. In the minimization problem into n lambda minus, and the minimization problem into the n lambda plus. And if lambda is between lambda 1 and lambda star, you are able to obtain a solution in each component. So you get 2 solutions to your problem by minimization directly on the component. And the next result proved that if U star is a minimizer of lambda star, when lambda star is the extreme value of the Hardy manifold, then the projection of this minimizer over n lambda star 0 is in fact a solution to your problem. So you get the first solution to your problem when lambda is equal to lambda star. But remember, we have to be very clear in the difference between the case considered by Chabrowski and Costa and the case that we are considering. So following Chabrowski and Costa, we introduce these 2 sets, L minus and B plus. Okay, remember, you have to find a way to avoid n lambda 0. You don't want to be there because n lambda 0 is not a natural constraint to your problem. So you have to avoid this company. And Chabrowski and Costa proved that there exists a positive delta such that if lambda is between lambda 1 and lambda 1 plus delta, then this intersection here is empty. This intersection is empty. So we go away, you are far from the n lambda 0. In fact, we prove that if lambda is between lambda 1 and lambda star, then this intersection is empty. So the same argument applied by Shabrowski and Costa holds. You can apply the same argument, the same technique. The problem comes when lambda is bigger or equal than lambda star. Then you prove that this intersection is non-empty. So here realize the big difference between the work from Shabrowski-Costa and our work. Because when lambda reach lambda star, you are not able to apply directly the arguments introduced by Shabrowski and Costa. So this was our goal in that time, to consider this case and obtain two solutions. But we have to change all the argument, okay? Until lambda star, open in lambda star, okay, but when we reach lambda star, the argument fails. So how to avoid n lambda 0? Okay, how to avoid this component? We introduce this set. I will talk about only about the first solution when lambda is bigger than lambda star. You introduce this set theta lambda plus, okay, and you use the fibering method of Pohozaev to project the points of this set theta lambda plus into the component n lambda plus. Okay, when you do it, you characterize the component n lambda plus like this. Okay, for each point in theta lambda plus, there exists a unique S lambda plus such that SU belongs to n lambda plus. Then you have this characterization. After that, you constrain the energy functional into n lambda plus. And you use the homogeneity of the terms in the functional to obtain this characterization here, J lambda plus, okay, can be written in this form. And you prove that if you have a critical point of this functional, J lambda plus, then the projection of this point is a weak solution to the initial problem P. The main difficulty here is to get this critical point, because the minimizer of this the minimization problem that you are working may not be a critical point. So what we have done, firstly, we proved that there exists a mu0 between lambda 1 and lambda star in such a way that each minimizer, remember now I'm working here theta lambda plus, each minimizer in which belongs theta lambda plus lambda star plus of J lambda plus satisfies this condition. But look, mu0 is between lambda 1 and lambda star. So what is behind of this condition is that we are separating J lambda star plus from n lambda star 0. Okay, if we get this minimizer, we are not in the n lambda star 0 because this condition here. Okay, but see, we are changing a problem to another problem, because our first problem was to avoid n lambda 0. Okay, we are avoiding lambda 0. But now we are minimizing into another subset, into another submanifold. But in this submanifold, we have boundaries. So when we are minimizing in this set, we have to be careful to avoid the boundary. We cannot find this minimizing the boundary. Okay, so we introduce this family of minimization problems, 8, and we prove that for each lambda and mu, we have a minimizer. Okay, but we have to be careful to prove that to find a suitable condition to conclude that this minimizer does not belong to the boundary. Okay, in order to do it, we introduce these two sets, S lambda mu and S lambda partial mu. Note that if we prove that in some situation, under some assumptions, S lambda partial mu is empty, then we are not in the boundary. So we prove that there exists a mu zero in such a way that S lambda star partial mu zero is empty. Moreover, we prove that since this condition holds, we obtain a positive epsilon such that S lambda partial mu zero is empty for all lambda between lambda star and lambda star plus epsilon. Okay, what have we done? Summarizing all the results that I talked superficially here without inside the technicality in the proofs. Combining all arguments that I said, we obtain a mu zero between lambda 1 and lambda star. We obtain a positive epsilon in such a way that for any lambda between lambda star and lambda star plus epsilon, we get a minimizer of H. A minimizer of H. This minimizer does not belong to the boundary, and the projection of this minimizer over n lambda plus is a solution of our initial problem. Okay? And this is the strategy to get the first solution, using the idea of the extreme value of Néhari manifold. The second solution is obtained by Montan-Pai's theorem, okay, but is not a direct application of Montan-Pai's. And summarizing what was the contribution finally, we know that when lambda is between 0 and lambda 1, we have a solution via minimization. When lambda is between lambda 1 and lambda 1 plus delta, Chabrowski and Costa proved the existence of two solutions via minimization by minimizing each component of Néhari manifold. And we proved that the argument holds until lambda star. When lambda is equal to lambda star, the argument cannot be applied, but we are able to obtain two solutions via minimization. And finally, we obtain the existence of a positive epsilon in such a way that if lambda is between lambda star and lambda star plus epsilon, we obtain a solution via minimization by the strategy that I comment here, and another one via Montan-Pai's theorem. That was the contribution of this work. But I said in the beginning of the lecture that this is a project, because natural questions arise, okay? And one of these questions is that possible to use this method to reach the threshold parameter to existence and non-existence of solutions? What I mean, is that possible to characterize a sharp parameter in such a way that until there we have solution, after that we do not have solution, say this is the guy. And other directions have been attacked. Professor Caio has studied systems in this direction, so we can adapt this argument in other operators on the class of problems. And I think my feeling is that in the next years we will find several works and beautiful results by applying this technique to get solutions and comparing the parameter with the extreme value of parameter lambda star. And I finish my lecture. Thank you, everyone and the presence. Thank you for attention, and wishing Merry Christmas and a Happy New Year. The picture with my son, Isaac. Thank you very much.